So today I'm excited to share with you a library that I've been working on for quite a while called Orbit.js, and why you might be interested in using Orbit in your Ember applications, especially now that I've released an integration library, Ember Orbit, just today, version 0.1. Conference-driven development. It's probably good for me. I'm such a perfectionist, I might have held on to it for another 3 months before letting it out. But anyway, it's up on GitHub now. So as Ember developers, we're not unfamiliar with pushing the boundaries of what web applications can do. I often like to ask myself, what's next? What's beyond this envelope? And lately, the answer that's been coming to me is autonomy. What do I mean by that? I'm not talking about some free-thinking bot that gains consciousness and passes the Turing test. I'm talking about being able to manage oneself and one's data independently of the server, not completely losing it when you go offline. Managing the user experience independent of the request-response cycle. Not blocking the user. This is often called an asynchronous UI. Those requirements require typically at least 3 data sources, one that's in memory, one that's in the browser, and at least one that's remote. And synchronizing those is not trivial. If we're going to provide a deterministic application, we need to start thinking more in terms of transactions, which are predictable. And they're also useful for developing a nice user experience in which a user can modify a tree of data, not necessarily just a simple object, but multiple related objects, and then either commit those changes or discard them. If we have a deterministic set of operations that are being applied with each change, then suddenly it's possible to allow for an undo and redo capabilities. We can push and pop off of a stack of transactions. Because I felt the current tools weren't up for the challenge over a year ago when I started working on Orbit, I started to look at solving these problems using primitives and plain JavaScript. These are problems that are not unique to Ember. The primitives that are used in Orbit are events, promises, and transforms. They're composed in some interesting ways. In a typical synchronous event handling scenario, the flow of operations from an emitter to a listener is sequential and synchronous and predictable. Once one of those listeners does something that's asynchronous, then it's no longer a deterministic operation. So say a listener then makes an AJAX call, you really can't predict from the emitter's perspective when that operation completes. So Orbit tries really hard to be deterministic with its data because it's trying to make sense of it. And it introduces a pattern of promise-aware events. It's fairly simple. A listener can engage in the resolution of an asynchronous event simply by returning a promise in the handler. And by returning a promise, then the emitter won't call the next listener until that promise resolves. And if this can happen over a chain of emitters and listeners, and you can actually add some determinism to an asynchronous situation. This is what I consider the async blocking scenario, in which each listener returns a promise. Of course, it's up to the listener whether it wants to engage in that resolution of that event, and therefore it could choose to return immediately and still perform an asynchronous operation. Of course, in order to be deterministic about the event itself, the emitter still needs to return a promise, because it doesn't really know what the listeners are going to do. And therefore, it can't be both synchronous and asynchronous at once. It has to return a promise. This pattern is used throughout Orbit's primary interfaces, the requestable interface and the transformable interface. These interfaces are really low level and can be applied to any object, any JavaScript object. The requestable interface is geared towards developer happiness. At the low orbit level, you can actually define any methods on this requestable interface that you want. These are the ones that are used in Orbit's common library, which I'll review later, but these are some examples. The important thing is that any of these methods that are requestable, if a source wants to engage with another source, it needs to implement the same methods. It needs to implement the same interface. So all of the sources that are involved in an application need to agree upon an interface as a contract. The transformable interface is pretty straightforward. Just transform. You could tell this guy doesn't pass the Turing test because he doesn't have rounded corners. So back to the requestable interface. What's the flow there? Let's say you have a requestable method, find. It's called on the source. First, it triggers an event, assist find. If any listeners engage with that and resolve the promise, then their result is taken as the result of the find operation, and it jumps down to the did find event at the bottom. Otherwise, the flow continues to the source's own internal find method. If that resolves, again, it goes to did find. If not, if it's not able to find a result, or it just doesn't want to, then the rescue find event is called. This is a backup plan. This is plan B for an event. And so you could set up, say, a backup source to handle methods that fail. And if any of these resolve successfully, then the did find event is triggered. Otherwise, did not find is triggered. The transform event seems simpler. The source's internal transform method, _transform is called. And the slightly tricky part here is that the transform operation that's requested may not, in fact, be the transform operation that happens on the source. And so did transform may be called any number of times with other operations. So you may think that you're looking for a particular record, a particular, say, in orbit, we deal with planets, just to keep with the theme. You're looking for planet 1. Well, when you request planet 1, the server returns its moons as well. Well, those moons would come back with did transform events because the internals of the source have changed The did transform event reflects any change to the internals of the source. So how does a source maintain its data? Orbit has a primitive document class, which is a complete implementation of JSON patch, in which there are different operations that are allowed. Add, remove, replace, move, copy, test. Those are all part of the specification. Transform is kind of a general method that can apply any of those operations. And retrieve retrieves data at any point in this document. The important thing to think of is that all of the data in a source can be modeled as a single document, and it can be accessed with a JSON path or a pointer to any point in this document, and retrieve can help you get that. So transform can help you change that document. Retrieve can help you retrieve its contents. Here are some examples of transformations. This is an array of remove adds, remove, say, takes a path. They all take a path. Add takes a value, which is an object. It's not too important to worry about these internals, but that path represents the JSON pointer to inside that document. So sources become more interesting when they're connected with other sources. The transform connector, of course, is for connecting transform events with, in one source with a target source. And they're only one direction. If you want synchronization in both directions, you'll need two connectors. Each connector simply has a source and a target. Remember our promise-aware events. Well, all of those events we reviewed are promise-aware, and connectors are listening for events. And connectors can choose whether to return a promise or not. And if they return a promise, then they're blocking connectors. If they do not, then they're in non-blocking mode. Request connectors help with the coordination of requests for data on the requestable interface. None of these connectors are absolutely necessary. You could, of course, write your own style of connector and listen to these events. They just help out with the process and have some internal intelligence for applying the transforms that happen in one source, say, to another. The default transform connector in Orbit employs a differential synchronization method because Orbit's agnostic about the back end. If you are applying synchronization strategies that are coordinated with your server, which you'll want to do for many types of synchronization, then you'll want to modify or write your own connector that is aware of the strategy you're using. So these Orbit sources, and Orbit itself is pretty primitive, which is why I composed them into a common set of sources in a common library. This is kind of a minimum viable library at this point. It has a memory source, a local storage source, and a JSON API source for communicating with a RESTful interface that supports JSON API. And there are others that people are working on, like an IndexedDB source, and and several others. You really could put a source in front of anything, like a WebSocket. The common library relies on a schema, a central schema, that's used by all the sources. so that they all are organizing their data in the same manner. The schema defines the models, relationships, ID fields. Sometimes you'll want a single ID field that's like a version 4 UUID that is that's unique, and that therefore you can just call it ID. Other times you'll want to have separate client-side IDs, which are just unique to the client, not necessarily unique globally. It depends on the system you're building. So you can define an ID field and a remote ID field. And there are other aspects of the schema. So before I get too much into the trees, let's step out and see the forest for just a little bit with a simple demo of orbit connecting two different sources. These are, we've got two different solar systems over here, and as we add planets to one, their operations are transforms complete, and those operations are synchronized with these transform connectors. They're set up. These are both enabled. These just indicate the flow. So there are two transform connectors between two different sources that are backed by local storage. So let's just add a few planets, and then you can see it works across adding and removing. It also, the stack is growing, and you can see that you can also apply the stack of operations, and you can pop off the stack and reverse everything that you've done. And you could do that in either place. Let's see, if you want to, say, apply changes to one side and not have those flow, you've disabled the connector, you've deactivated it temporarily, but changes to the other side, that connector is still active, and since they have a common ID, if you delete one from the one side, they delete from both. So it's just a simple example of sources, synchronization, and what you can do with a transform stack, like an undo operation. So let me get back into this new integration library, which is perhaps most relevant here at Wicked Good Ember to talk about. So let's see. The source is actually a pretty loose wrapper around the Orbit Common Libraries source. It simply extends, you define a source that extends a base source class. You can define the Orbit source class, like here we're linking it up with the Orbit Common local storage source, and set some options for that source, like the namespace for local storage. The store might look more familiar. It extends the source, and it maintains an identity map of model instances. It's really what's meant to be interacted with from the perspective of an application. And it has interfaces that are quite close, where possible, to Ember Data's store. I really respect Ember Data's API, and I think a lot of those interfaces are really well designed, and I've tried to keep Ember Orbit's interfaces as similar as possible without compromising on what's possible with Orbit. So the stores methods involve synchronous methods that can access records within it. All filter, they are very similar to Ember Data Store. They retrieve a live record array. So if you retrieve planets or planets that are terrestrial with a filter function, those will stay in sync. as planets are added that meet those filter criteria. Retrieve simply grabs a single object from the store. It's actually, and returns that as a model. Asynchronous methods, again, are basic CRUD methods for both the records and relationships. The model itself helps define the schema, and this is really important. It's backed directly by data in the source. It doesn't have its own data property. Its data comes directly from the orbit source. But it does provide familiar interfaces to access that data. So here's a schema. We're defining stars and planets, and a star has many planets, and they all have names, and this planet has one sun. Now, this is the only case where I'm going to troll Ember data at all, but there's no distinction from like a foreign key perspective between, say, has many and has one. So I couldn't bring myself to name it belongs to, like in the Ember data interface. So anyway, you could alias that if you like. The model also has synchronous methods to get and set data, which you'll probably want to use most of the time. But if you want to monitor an asynchronous operation that's happening in the background, a request, then you can also call directly an asynchronous method on that model. Here's an instance of adding a planet, Jupiter, and when that resolves, we're grabbing its moons. It has many moons, its relationship. We're pushing in another object we've grabbed earlier, that's Io, the moon. And we're setting the classification of Jupiter to be a jet gas giant. And then this is an interesting aspect, store.then. Remember, all of the requests are asynchronous. And even though we have some synchronous methods to access properties and relationships, these are accessing what's currently in the store. But the result of an asynchronous operation isn't known yet. So the store itself acts as a promise, which can be resolved when all requests that are outstanding to it are resolved, in which case you can then see that the inverse operation of adding Io to Jupiter's moons also set Io's planet to Jupiter. So again, I want to drive home the point that just like in Ember, URLs drive application state. In Ember Orbit, sources drive model state. None of this would be possible if models were maintaining their own data outside of the source. None of the really interesting things you could do with Orbit are possible. So let me bring this back to the title of the talk, Autonomous Web Applications. We've seen a lot of details, a lot of APIs and such. Let's talk about some applications. Well, all of these sources have the same interface, and therefore you can plug them in one for the other. If your browser allows for IndexedDB support, you can load the IndexedDB source. Otherwise, local storage is your fallback. Sources can replicate their contents. You can create a clone of a source, including all of its content or just the content you want. And then you can either connect it back to the original source or not. But that clone can be operated upon through the user interface. And you can gain some control over when those changes get applied back to your canonical source. And as you've seen from our demo, you can also track operations, track the low-level transforms that occur with any request, and you can then keep a stack of them and undo them or redo them. And those connections can be set up and customized to provide synchronization which meets the schema of your full stack application. So what's the status of Orbit? Well, in a word, it's alpha. Orbit itself was just released in January, and it's now at 0.2, which comes shortly after the tinfoil release. I'm firmly into the first batch of stickers release, anyway, an Ember orbit itself was just released a few hours ago, and it's 0.1. So there's a lot to do. Orbit itself needs more sources and more synchronization strategies. And I'm sure as those are added, some interesting architecture implications might come up. Ember Orbit itself does not fully encapsulate Orbit's API. It would be nice if everything was Emberified. It really needs some improved ergonomics. You immediately notice that if you're dealing with a remote source and you have to drop down to serialization, and you have a single method called serialize and another one called deserialize that you have to completely write. This does by no means provide the ergonomics that Ember Data's serializers do currently. I would like to wrap these interfaces as much as possible and expose them in ways that could be seen, that would have nice conventions and nice ergonomics within Ember. So pretty soon, I'd like to launch a site for Orbit, which includes API docs and guides for both Orbit and Ember Orbit. In the meantime, please feel free to track progress at Orbit.js on Twitter or in the two Orbit and Ember Orbit GitHub repos. That's it. Thanks a lot.
I knew Steph would add a question. Okay, just pass.
So the store.then, you said it gives sort of a state of the world at some point in time. What decides what that point in time is? When is the world or that store stable to present it to the user?
So at that point in time, there is an array of requests. I'm sorry. At that point in time, there's an array of requests that have come in. And that array is resolved with rsvp.all. And as those are resolved, they're popped off that array. So it's whatever promises are present when you call then.
Okay, so basically, if there are pending things at the time of then, it will take a snapshot of the array, wait for that array to flush,
That's
then
right.
invoke. And if subsequent things happen, do you hold them off before they get applied? So if you get subsequent requests while you're waiting, do those requests get held off until the then is invoked and then they're applied after the then? Is that the idea?
The RSVP all is called with the array in the then method. So it's that array of promises that's in the method at that time.
Okay, thanks.
Yeah.
Hey, Dan, awesome progress on this. Question about conflicts. Does Orbit at this point handle when sources change in different ways, say between two users on different browsers, and then kind of like along these lines, the concept of operational transformation, where does that fit in with Orbit, if at all?
Right. Okay, so I did mention that if you might want to, if you have a full application which has a synchronization strategy, you're going to need to modify the connectors. The connectors provide a place to reason about synchronization. They open up that logic so that you can apply a strategy based upon perhaps a a key, a timestamp. These are complicated issues, but depending upon your particular application, you need logic to resolve the differences. Right now, what's resolved works well in the browser, but I wouldn't deploy it with confidence because people will be stepping on each other's toes unless you have a synchronization strategy that you're confident with that's through the full stack. So that's really an important point, and thanks for bringing that up, Luke.
So I have a question about the document API. You're using JSON patch operations as sort of fundamental transform steps.
Yeah.
Does Orbit provide facilities to linearize the operations? So what is keeping, does it have a facility for this add has to happen before this remove? Or is it meant to operate in the messy environment where one can arrive after the other?
So each source maintains a queue of operations, and that queue is performed as they're added to the queue. So those operations would be performed in the order they're added to that queue.
Okay.
So yes, we are very concerned about the order of operations.
Hi, Dan. This is more of a statement than a question. Apparently, I've been working on the same idea independently.
Really?
I have been writing it frantically in my notebooks and laptop for the past week or two, and people have been telling me I've been having a manic episode, but this is the most exciting idea I've ever come across. And I've solved some of the problems that you haven't, and vice versa. So I'd love to catch up with you at some point while I'm not having a manic episode and talk about this
That
calmly.
is so awesome. Yeah, I love putting this out there and hearing from people like you, because I'm sure that together we can build a heck of a lot better solution than myself working alone. I've been working alone on this too much. It's time to open this up and bring people in. So that's exciting. Thank you.
Great, thanks.
Any more questions? Anybody else? Okay, all right, thank you, Dan.